In this last video related to gases, we are going to look at aspects of the kinetic molecular theory, talk about the speeds of gas particles, and then wrap it up with what makes actual real gases different from ideal gases. First off, we have this animation in front of us that just simulates what particles in the gas phase look like. Notice they are in constant random motion, they're colliding with each other, and the pressure is due to the collisions with the walls of the container. You'll also notice that there is a distribution of speeds. Not every single particle is going the same speed. If you focus on just one, it's different than the others. You'll also notice some differences between the smaller red spheres and the larger gray spheres that actually starts to get into what makes ideal gases different from real gases. Okay, so there are two new equations to look at for today. The first is a calculation of what's called the root mean square velocity. We symbolize this with the letter U, usually abbreviated RMS, and it's equal to the square root of 3 times R times the temperature divided by the molar mass. The most important thing to get out of this equation is conceptually, all that matters about the speed of a gas is how hot it is, the temperature, and how heavy it is, the molar mass. And I'll make a note here that the molar mass has to be in kilograms per mole. Normally our molar masses are in grams per mole, but you'll see in a moment why we use kilograms. This is also not the same R value that we saw with the ideal gas law. Here R is a different number. 8.314 because we're using the base unit joule per mole Kelvin instead of a liter atmosphere. R is 0.08206 in PV equals nRT. There are many other equations that actually use a value of R and we convert it into the unit of joule. You'll see that later on throughout this year. So conceptually, this is actually illustrated in this graph of distributions down here. This shows speed distributions. In this case, it's at different temperatures. And what you should notice is that at higher temperatures, as T increases, speed increases. I can see the x-axis increasing as I increase from 300 Kelvin to 600 Kelvin to 900 to 1200. There's more and more particles underneath the curve at a higher speed, and also the distribution widens. In other words, at higher temperatures, there's more variety of gas speeds in a given container. Let's actually use this equation right now and calculate the root mean square speed of nitrogen molecules at a certain temperature. So I'm just going to start by copying this equation, U, RMS, is equal to the square root of 3RT over MM, and we'll substitute and solve. So radical 3 times 8.314 joule per mole Kelvin. My temperature in 25 degrees Celsius becomes 298 Kelvin. And then I divide by a molar mass. Now it says the molar mass has to be in kilograms per mole. So remember, nitrogen weighs 28 grams per mole, so that becomes 0.028 kilogram per mole. Why do I have to turn it into kilograms? Well, it has to do with the fact that these units at first don't look like they all cancel out. I need to, for the first time in this course, focus on what the heck a joule is. A joule, if you know from your physics class, 1 joule is a Newton times a meter. It's a force times a distance. And a Newton is a mass times an acceleration. So it's a kilogram times a meter per second squared. And then we have this other meter from the Newton meter. So that's what I'm actually going to substitute in for my joule, which means there is a kilogram meter squared per second squared for every joule. And I'm going to write that as a conversion right here in the work. For every 1 joule, there is a kilogram meter squared per second squared, and let's look at what happens to our units. We just canceled out the joules. My per mole cancels from the molar mass. Our per Kelvin cancels with the Kelvin temperature, and now our kilogram cancels as well. We're left with meters squared per second squared, and then we're going to square root it, so we're going to get a number that is in meters per second. In this case, you get 515 meters per second. So pretty fast at room temperature. Gas particles are quickly moving. They bounce off of each other and they collide with the walls of the container, so they may not cover a whole lot of distance, but their individual speeds are quite large. And the hotter they are, the faster they are. And the heavier they are, the slower they are. And that is exactly what this picture over here is meant to depict. These are distribution graphs, which show any number of gas particles can exist and how many of them exist at these various speeds. So it's the area under this curve, or imagine a lot of different bar graphs underneath this curve that we're looking at. You might be wondering, what the heck is a root mean square velocity? Is that the average? Not quite. It is very similar to the average, but it's actually defined as the speed of a particle whose kinetic energy is equal to the average kinetic energy of all the particles. It's similar enough to the average, so you can think of it that way, but it's technically not. It is different than the average speed, but we use it that way quite a bit. There's a second equation we're going to use today, and it's actually derived from the first one. It's about relative speeds, the relative rates of what are called effusion. R1 over R2, those are rates of effusion. Effusion just means the movement of a gas particle through a small opening. Picture a pinhole in a balloon and a gas leaking out of it. That's something we can measure. For this class, we're just going to talk about the relative rates of effusion, and it's equal to the square root of the ratio of the molar masses, but inverted, molar mass 2 over molar mass 1. So I can tell how much faster or slower one gas is compared to another one at a given temperature just by the ratio of the square root of their inverse molar masses. So I want you to hit pause right now and use that equation down here. This says consider methane and helium. First of all, conceptually, who do you think is faster? And then quantitatively, how much faster? Hit pause and try that now. Okay, so helium is much smaller than methane. So lighter molecules effuse faster. So that means helium should be the answer to this question. And we can quantify this. How much faster? The rate of helium relative to the rate of methane is going to equal the square root of the molar mass of methane, divided by the molar mass of helium. Methane weighs about 16, helium weighs about 4. The square root of 16 over 4 is about 2. So what that means is that helium atoms effuse twice as fast as methane molecules. That's what Graham's law tells us. And that's actually all you're going to be asked to do for the purposes of the AP exam. Graham's law comes from the root mean square equation, so I wanted to show that, and you'll certainly see that in future college chemistry classes as well. Okay, so to wrap up this unit, let's talk about real gases. How are real gases different from ideal gases? Remember, gases behave ideally at high temperatures and low pressures. It's when they look like gases, very hot and very spread out. You know, in this simulator, if I go back to here for just a second, an ideal gas looks something like this, with infinitesimally small particles. The volume that the gas occupies is much more significant than the volume of the actual particles. We also shouldn't have any interactions of the particles, which this simulator does a good job of showing what really does happen. Particles do cluster together, like I can start to see the interparticle attractions that the gray spheres have, but that the red ones clearly don't have as much of. And that's what makes real gases different from ideal gases. Gases are less ideal when they have those strong attractive forces. We're going to get to what types of forces those are later on, but this causes them to cluster together, and as a result, they exert less pressure than predicted by the ideal gas law. So if we see a deviation where the observed pressure is lower than what we're going to calculate, that means it's likely due to the fact that there are strong attractive forces with those gas particles. The other deviation we see is that gas particles are less ideal if they are larger, because then the volume of those particles is no longer negligible and we observe more volume than what would be predicted by the ideal gas law. That's actually illustrated over here in this graph that compares the Boyle's law relationship, the pressure-volume inverse relationship for an ideal gas versus a real gas. And what I want you to make a note of is that at higher pressures, particle volume becomes significant. We think of gases as having infinitesimally small particle size. The molecules or the atoms themselves are negligible in terms of their own volume compared to what space they occupy. But if you compress a gas down to a very small space, such as I'm doing here, all of a sudden the particle volume becomes very significant. And we can see that if we compare how much more volume we observe in this real case versus in the ideal case. And that's just what this graph is showing. And let's just wrap up by showing a picture of what an ideal gas particle diagram looks like versus a real gas. Ideal gases are infinitesimally small particles. I'll just draw dots in this box, as opposed to real gas particles, very exaggerated, but much larger. They actually have volume and they have interactions. So particles in an ideal gas, particles have no volume and no interactions, but in real gases, particles actually have volume and they interact, causing those deviations we mentioned up above. So the volume that we would measure for a real gas is often going to be greater than what we see for an ideal calculation, and the pressure of a real gas is often lower than the pressure predicted under the ideal gas law. Okay, so that talks about how real gases are different from ideal gases, how we can calculate the relative rates of effusion for different gas particles, and how we can even calculate the root mean square velocity of a gas particle based on its temperature and its molar mass. And that wraps up our gases unit. Thanks for watching.